Okay, so let's continue our training session here, our live coding. So the last time we kind of finished to write the main function of our little Welsh structure, so to compute a periodogram. So to recap, we did the segmented of the signal with overlap using already iterators. We see how to do Fourier transform in Rust, something which is quite common in our line of business. So I think it was useful to have an idea of how to do that. And then in this little line of magical code here, I'm able to take the Fourier transform of all the segments, compute compute the magnitude of the complex numbers here, and sum them in quadrature.
Rod, are you trying to share? Are you trying to share?
I'm trying to share my screen. Sorry. This time I remember to record, but I forgot to share my screen.
That's okay. Now we got both of them going. Good.
Okay. Yeah. Sorry. I was so much in my way. Here we go. Yes. Sorry. So no, it makes sense, right? So I was going through the different steps we went. So we have four methods. We have the new method. Maybe I can zoom a little bit more. Maybe you see better. The new method, the segmented method, the DFT method, which called in fact the segmented method. I think yes, and we have the periodogram method. We spent in fact the whole session discussing that this iterator, the fold iterator, which is quite powerful when you get to understand it, how it works. And that, in fact, it's an iterator inside. And here we makes it a bit more complex because we have an iterator inside the iterator. So before moving on, is there any question regarding what we've done so far?
Just a reminder, I don't know if all of you are aware, Rod shared the latest version of the example in a GitHub repository. I can copy the link.
Thank you. So now that we have our main program, our main library available, we decided to now start to test it and see if what we're getting makes sense. So we're going to build an example, and the rest environment is well structured, and you're free to adapt to whatever you want. But it's recommended to follow it because it's really well done, and it has a lot of tools which are mapped to the structure of a project that they encourage. So last time I did show you that you can, to create example, you just have how you can create an example directory, and that's going to be where one of our main application are going to reside. So if we go to example here, so right now I put just an empty main function, and if you recall, to build a library, we did simply cargo build, right? Now if you want to build an example, you just add example and the name of the example, and we call it this one Welsh. So this with cargo, again, you can use it to build and run your applications. And it helps you organize your code in a way that makes sense. I show you here the tree of code. So now we have the sources directory where we have the library we wrote, and we have the example that are going to be there. And you can have, if you read the documentation, you will see that there's other directory you can create with other purposes. Okay, so in order to exercise the Welch algorithm that we have implemented, we're going to need to define to write first define the signal, and something we do very also often is plotting. So I will show you how I plot in Rust first. So first step, we're going to write a signal, plotting it. Maybe we can add noise too. Noise is something also very common. So we good to see how we can do that in Rust. And then we can apply the Welch algorithm we have implemented. So let's define a signal. So again, we call a variable. We define a variable with a signal with a let keyword, and we're going to use again an iterator here. So we're going to go from. So what is going to be our signal? We can go for a simple sinusoid, something like that, 2 pi, or let's go for the LaTeX syntax, 2 pi time and times the frequency. So we're going to go f0, for example, something like that. And we also need to define the sampling time. So we're going to define index and multiply by tau, which is going to be our sampling time times the frequency. That would be the definition. And I usually prefer to define that as the inverse, or the sampling frequency is something we are frequency of our signals. So that will be what we're going to implement, and we're going to have I frequency, and I should go from, let's say, 0. If we go from 0 to 0 to sampling frequency divided by f0 again, then that will be a full period, if I'm not mistaken. Yeah, I think that makes sense. If we want to, yeah, it will be from 0 to 2 pi. Yeah, makes sense. So let's implement that in Rust. Okay, so how we can do that? Let's define first a few parameters. So we need the sampling frequency of our signal. So we need to sample it, let's say, frequency at 1000 Hertz, like that. The Rust has quite a friendly syntax, so you can write it 1000 like this, but sometimes it's more readable if you it's an extra. I like to do that way, and I don't think that would work. We need to do that like that. Or you can put a type in front, like he did here. Like he did for me. You see my editor that did it for me. I didn't write it. And okay, sampling frequency. All right. Oh, we need also the f0. We're going to put that at maybe, I don't know, 20 Hertz to start with. Oh, I will show you something. I will do it different, slightly different, so that you can see the typing. So if you do it like this, it's complaining. You see the type of, you need to always put the type of the variable, and you can put it either at the end of the when it's a scalar like that, or you can put it at colon at the type. I mean, you can, so it's up to you. Here it complains. What is saying?
There is a typo. I think it's F9. It's Zero.
F0. But it's not a typo that is complaining.
Also an E missing from sampling frequency in the let statement.
Thank you.
But yeah, but it shouldn't be complaining about that.
No, it's not complaining. Let's see what it, I think I know why it's complaining. Cargo build example. Yes, because 20 is seen as an integer by the compiler, and I say I wanted a double. So that's why very often I prefer to type it like I did before, with a type at the end. Otherwise, you just need a dot here and you understand that it's a floating point when you do the conversion. But that's why personally, it's a personal preference at that point. I prefer to do it like this. But that's me. It's a safer way to do it. Okay, so we have that. Oh yes, we need to define the number of steps we're going to go through. So we say it's going to be sampling frequency divided by f naught, and they are both floating point, and we want that as an integer, or better as an unsigned integer. And the unsigned integer is so common in Rust that they have their own data type for that, for usize. It's a very generic unsigned data type. So here we'll have about 50 steps, right? So 550. Am I doing right? Something wrong here? No, maybe it's okay. We'll see. Doesn't matter. We'll see when it plot. And so now we have that, so we can define. So how you would define a signal like this in Rust? So we again, it's an iterator. We're familiar with those. So this what I just typed is a range, and a range is already an iterator by itself. So you can some type in Rust are already considered an iterator. So you see my iter recognizes it's a range of a value of type usize. So we're going to iterate through that, and so we don't need type iter because it's already iterator. So we just can call the map function on the iterator, okay? And the function we're going to use, which is going to be I, and our signal is then. Put it below, maybe easier to see. So we need Q as floating point multiplied by pi. So that's pi is available in Rust. It's a bit hidden in the standard library, but you can get there const pi, and you see there's a bunch of other ones that you can have access to. So we just need pi. 2 pi multiplied by I, which is a usize, but we do everything in floating point. We just cast it like this, as before. Multiplied by we said f naught, and divided by the sampling frequency. Okay, and we need to apply this and take the sign of that. So contrary to many languages, we apply the sign at the end. And if you have followed the first session, you realize that when we define a structure, we'll have the object and the method apply. So that means that the type f64 is also an object, and you can apply function method to that. So that's why you put a sign of it. So it's how we get the sign of 2 pi I f naught divided by sampling frequency. And an iterator like this, you see what the type is returned. It's just an iterator. So we don't get exactly what we want. We want an array. So we want to collect it at the end. Force the iterator to go through all the value of I. Otherwise, you just get an iterator, but it doesn't do anything. Which shows that an iterator is also a kind of variable that you can carry around and execute it when you want. So you can even pass it to function and so on. So that's pretty powerful. And we say, okay, we want a vector of F64. And that should compile. Yeah, that compiled. And we can also sometimes let the compiler to guess what should be the type. And here it's obvious that we're using F64, so the underscore here will tell him, okay, figure it out, and effectively he's able to figure it out. All right. So we have our signal. It would be nice to plot it to make sure that we're getting what we want. So let's see how we can plot in Rust. So you see, this is a favorite website that I like to go to look for third-party application. If we look at what we have in terms of plotting, do we have? Yeah. So Rust is still a relatively new software, so there's not a well-established plotting library. So the one I like to use is Plotters, and there's some nice example and some nice documentation, incomplete, but you can still do a lot with that. That's the one I like to use, and I wrote some wrappers for plot because it's a bit verbose. So there's something called complot that I wrote, which is still in development, but that's allow to plot in Rust in just a few lines of code. But let's see. Looking at the example I put online here. So let's see what I'm doing here. Just oh yes, okay. Let's adapt that to our example. So I will do it and I will explain. Let's do it that way. Oh, I forgot something. I need to tell Cargo that now we're going to depend upon this third-party library called complot. There we go, and it does it. So now if I do Cargo,
you also include the use in the main.rs.
Yes. Yes. Where did we go? Ah, here we go. You can, but I won't do it to show you. It works without what you don't really you don't always have to do it. Because as soon as you add it to Cargo, the package is available in the workspace of your application if you have complot already. I think that makes sense. Let me try to compile the library, Cargo build. Oh, let's spend a bit of time on that because, okay, you see, it downloads everything that complot depend upon, and I'm going to build it. All right. So there's something interesting here that I realize that I'm going to spend some. We need the library for the example. Sorry, we need the plotting library for the example, but for the library itself, the core algorithm, we don't need plotting there because it just so adding this extra library with all this dependency to the Welsh library is not very convenient, right? So if you go back to look at Cargo, you see it added complot here in the list of dependencies. But we don't really need the plotting library to compute the Welsh algorithm. It's just for the example. So Cargo can give you an option to add only the complot and its dependency for the example. So let's remove complot now from the library. So it disappears from Cargo now. The Cargo build will work like before, and we're going to add it again. Cargo add, But if you, with the D option, which is for development, if you do that, if we look at cargo again, cargo, you see now it's a development dependency. Now if I build my library, it does nothing. But if I go, if I build my example, okay, let's stop it because that's not obvious. Let's go clean plot. Let's remove. Let's pretend we never installed complot. There we go. And now if I build my example, yes, now you see it's done only complot and compiling it. It was already downloaded before, even for you. So you see the difference? The nice thing is that you can add, sometimes to test a library, you need to add a lot of third party, like adding some plotting capabilities, and maybe adding some property, we'll see some other crates for noise, but you don't need the main library to be bloated with all that, so you can separate like that. Okay? It was nice to see. Okay, let's go back to using complot. So let's see. You see, Rodrigo, I'm going to use the base of the namespace like this. Complot equal. Okay, so we got a plot from complot, and we go a plot from the signal. And again, I've found a iterator, so I'm going to put that into an iterator. So I'm going to consume it here instead of. If I do just iter will go through reference of each element. If I go into iter, it goes through each value of the element. But that means the signal won't be usable after that. I may spend a bit more time explaining that a bit later. Into iter, we're going to map, and we're going to enumerate. We're probably going to need a sampling time here, which is vector equal the inverse of the sampling frequency of the reciprocal. As a function, you can do 1 over sampling frequency, or you can use a function which exists. Enumerate. Okay, so that gives us an iterator with a tuple which has an index coming from enumerate and the signal value as 64. Okay, oh, yeah. You see what I was saying too. You see the signal is S64. If I go to iter, you see it's changing to ampersand, so it's a reference. So, but here I want to consume it. Okay. And so map that, and I need to do that. Bear with me a minute. So get to as F64 equal 2. So this is our time variable. And in the vector, we're going to put, we're going to explain the minutes. Vector of S. Oops, okay. So that's an iterator. And I think I just need to put none. Put that in a tuple. And do into. Oh, yes, I forgot to put that. There's probably some warning, but that's okay. We don't have. So if I build that, I'm going to go back to the plot in a minute. I just want to run it, making sure it's working properly. Like that. Aha! And we have a complot.png. Why we don't have complot.cv? Maybe there's a bug, but let's see if I can fix it later. Ah, here we go. Just plot a sinusoid. Fantastic. Okay. Let me go through, explain how we did that. So what I did is, what's the little complot wrapper. Let me explain a bit more because probably it's a bit difficult to read. So what we did here.
Can I make
So-
probably a silly question before?
Yes.
What does the dot receipt does with the sampling frequency? What's receipt?
Reciprocal. It's 1 over
Okay.
sampling frequency.
Okay.
No, it's a good question. There's no say. You can use 1 over sampling frequency if you want to. That's, I just wanted to illustrate this function. So what I did with the iterator is I create an iterator over the time and the signal that I put it in an array. So complot, you know, if a plot that we for complot, you need for to explain that properly. You need for each point or each sequence in the plot is going to be the x axis and the y, the x value and the y value. So t is our x value and f is our y value, and I put that in a tuple, and I provide an iterator of tuple like this. You get each point. I put the y value into a vector because sometimes you have multiple plots. So for the same x, you may have several y. So that's why I put that in a vector. So it's what I'm doing here when I do the mapping here. That makes sense. On this part is really doing that.
The enumerate gives you the x-axis data.
Yes, enumerate on an iterator give you a counter, which increment as you go through the iterator. So I use that to compute on the fly the x-axis, y times 2 sampling time. And I won't do it now, but you can set up I may do it later, the label for the x and y axis, this kind of thing, by passing some variable to instead of none. I don't. Per default, you do anything. You don't do anything. You just save it to a file that is named complot.plot underscore plot.png per default, and that's about it. Okay.
I have another question.
Yes.
When you used the -g to include the complot crate just for development,
Yes.
is that does it appear just in the cargo.tml in the example folder?
No, you can. It applies also. You can create a test folder also. Something.
Okay.
First, put an emphasis on testing your software, and you can do inline testing or testing in a different folders, and that applies there too.
I'm making this question because I saw some examples where there is probably we can say a main cargo HTML in the main in the higher folder in the hierarchy, and in some subfolders there are some local cargo HTML, and I didn't know if that was you are doing, and apparently
No.
It's not.
It's not. No, you can have complex hierarchy. You can have nested crate or you can define. You can have nested crates, or you can have a workspace within a crate. And they are different. A workspace, all workspaces share the same library. Nested crates, each nested crate is independent on the others. So depending on what you want. You see here, I just put five beatings of the sinusoid. I just increase the number of steps by 5 and update that. Easy. So just like that. I don't know if you have any more questions on the Complot library, but
yeah, just one. So is this figure saved on your computer right now, or is it only displayed?
It's saved. You have to open it yourself. You won't open it by itself.
Oh, okay. And then you have to clean that up. Or
Yes,
where is it
yes.
saved?
Where you compile, where you run your program.
Oh, okay.
Can you put like labels on the X and Y axes as well?
Okay. Yes. I will do it now because it's something that the question came twice, so that's something. So you can use Complot again, and the simplest way to do that is to use there's two ways to do it. Let's do which way? Let's go the verbose way first. So I think it's important to know, yes. So there's I wrote it, this wrapper, such as, I like plotting library which separate data from the configuration of the plot. Very often they are a bit mangled together. I like to have them separated. So the iterator here allow you to, so the first part of the tuple is really your data, and the second part is going to be some config of your plot. You really separate them. So it's why it's a tuple. And the into function, yeah, it's allowed to convert this tuple into the plot itself. I may explain that a bit later. And the config, config. Again, you use Complot. Config, I think. New. Like that? I forgot. I think it is. And we can do X label. No, it's not like this. You define an axis, and you do axis. I think it's like this. But maybe I should go back to my documentation because I forgot. Axis property. Or we can do it. Yeah, this is the simplest way to do it, but I want to show you both because it's useful. Oh yeah, like that. It's like that. Okay. And config. No, let's combo. Config. New x-axis. Okay, that's what I was looking for. Define one. Define x-axis, and we can define Complot. Define the point axis. Define the point a new dot x label. X label, and this is going to time in second. No method, why is there no method? X-axis. Oh, it's just label, yeah. Because for X and Y axis, it will be label. Okay. X-axis. So as you show, always write your documentation, even for yourself, because you forgot what you wrote. And we have a little label now. I don't know if you can see it. It may be small. You can try to zoom a bit. But yeah, you have it like this. So it's a way to do it. So it's a bit verbose. So another way to do it would be simply to do Let's go back to my documentation. Let me show. Right. Ah, yes, use this macro here. So instead of using that, I could go directly online here. So the config really is a more versatile way. What I wrote here is really a very versatile way to do it. But for quick and easy, you can just use the complot macro. Complot macro. Here you have to specify the file name. So we're going to call it welsh.png. Signal. Signal.png and x, and this time say x label. Yes, x label equal time of s. Ah, yeah, I think that's even simpler like that. That's all that for us. Yeah, it does it. And now it creates a signal.png file, which is the same as before. So you see, this is a bit nicer, this macro. You don't have to go through all the steps of defining that. But it does the same thing. It's just a shortcut, right? For example, you can also put legend, not on the version which is currently on the public website, but for example, you can put legends through this syntax here, but not with the macro. In fact, the macro expands to this syntax, but it's for quick and dirty plot. Macro is very useful. So, okay, that was a good question. Or maybe we can try to apply already or Welsh on this this is a sign user. Let's try. Let's see what we're getting. Let's go to the link. Okay, so here we're going to use. So to import, so I could have used use complot and import individual module, but I didn't do it. But we're going to do it here for our Welsh crate. So example is really a really independent application, and you use your library like if you were outside of your library, and we're going to call Welsh. Okay, and let's define. We're going to call that. What are we going to call that? Can we call? Yeah, we can call Welsh. It doesn't matter if it's the same name as. Well, it's a lot of Welsh. I don't think it's going to matter, but I want to confuse. Let's do PSD. And we get new, and we want to maybe use for many segments. So we need n segment, 4 segments, overlap by 50%, and we want to pass our signal. Yes, that's going to work. Interesting. And yes, of course, I need to specify that we want to. That's coming from Welsh. Okay. Okay, that's not going to work. The syntax is correct, it's just something else I will show you. Let's do it first. You see, the compiler is quite useful when you're familiar with it. It says signal, the value is used here after move. And so, and you look above in blue here, the signal moved due to this into iter method here. So here, I move the signal into my iterator. So it's consumed, so you cannot reuse it anymore. It's different from what Python is doing. It seems a bit over constrained, but it in fact removes a lot of bugs you may have from other stuff, even in Python. So better to use a reference. Go ahead.
Is that because the access in Rust is a destructive access? And in all
Because
of the
what, sorry?
cases, this is the case. Destructive access. I mean, every time that you try to access something in the memory, you consume that and it's not available anymore.
No.
No, that's
You,
not the
you,
case.
you, you, you can define by reference too. It's what I'm just did here. You see, changing into iter.
Oh, okay.
You see, the element of S was F64. Now I'm going to go to the signal as a reference. So now I have a pointer to the variable in F64. Right? You see the difference? So that's what it does. But now I have another problem, which doesn't compile here. The problem is no longer here. The problem is here. Here, what is expected, it's not a vector of a pointer to a variable, it's the value itself. So like if you're familiar in C and C++, when you have a pointer to a variable, to dereferences, to get access to the value behind the pointer, you just put a star, and the same applies to Rust. So it's same idea, and that's compiled. So you see the difference. What I did is I create an iterator by reference. So I get now address to the memory where each element is, and I tell Rust, yes, but I don't need the address. Here I don't want the address. In fact, I want the value behind the address. So that's what the star means. For dereferencing. Okay. Any question? And we can just call periodogram now, because periodogram called DFT, which called segmented. So we could do everything we need to do. Let's see. PSD dot periodogram. There's no input, no, just like that. Yeah. There's no compile, there's no issue. Okay. There's a warning because I put yeah, I do. Well, yes, I did something here that it's a leftover when I copy and paste. I don't need that. So for this code, yeah, that's simpler. Yeah, okay, everything compiled fine. So even if it compile in Rust, if it compiles, it runs. So it's the same as doing it runs. Good. Okay. So okay, but how do we get access to a periodogram? What do we do with a periodogram? Here. That's been silly. We computed the buffer, but no, the buffer is out. Yes, it's out of the program. Okay, so we need to get our PSD out. So we're going to call it, or maybe you can call that PSD. That would make sense. And I don't know how to call that. I will call it Welsh. There's too many Welsh, but you see, it won't collide with. Even if we call the. Oh yeah, I didn't know it's called Welsh here. Welsh. It doesn't collide. It's very well. Everything is well segregated in the Rest. Okay. So we have it. We can try to plot it. So we can try to plot our signal. Oh, we're going to need to compute the frequency of our signal. So if you remember the frequency, that's our signal. So our signal, let's try to go the frequency online. Let's frequency equal. So the frequency is going to be there's as many samples as the length of the PSD itself. So PSD dot length, okay. And we have an iterator, and we need to take that. And I as again a tuple, and I need to multiply that by the sampling frequency, I guess. Am I right? Am I wrong? I think, right? That will give us that. Right. And we collect it again. Oh, we don't even need to do that, but that will be the size. But take like that. I forgot that. Here we go. Voila. So we have our frequency vector now. Okay. We're going to try to plot our signal now. In fact, we can use again our PSD here. In fact, I don't really need to create the frequency. I can create the frequency vector on the fly. Now we understand what it is. Multiply by sampling frequency. I think it's right. We'll see. The vector of S, which is the same thing. We're going to call that PSD. The label should be the frequency. Frequency in hertz. And we don't want we want something like logarithm on the y, a linear on the x. It will be easy to read, so we can call something called lin log instead of lin. Plot is a lin. And let's see if that works. Can I run? Oh, it did it. Let's see what the PSD looks like. Okay, I must have done something wrong with my sampling frequency. We have a peak. I don't know if it's the right place. So we have sampled that. I got something wrong with my frequency calculation. Let's think a minute. Because we're sampling at 500 at 1000 hertz. So we should be sampled at 500 hertz. What did I do wrong here? Just a minute to think about it. The simplest silly thing to do would be to... just a minute. Okay, I just need to take that. I will be with you shortly. Sorry.
Hey, you guys, what's wrong with this code there? Any ideas?
Doesn't he have to divide by the sampling frequency?
Yes, if we look at the range of the frequency, it's wrong. So probably.
Yes. Sorry. Okay. Yes. That's. For a signal with a given sampling frequency, you expect to have half that, and we're going to go. Oh yeah, we're going to do like that. Divided by how many samples do we have? The size of the window. And it's one PSD dot lamp. And as F64. That will give us, yeah, that should give us up to 500 hertz, which is what we are expecting. Yeah, okay. So we go to 500 hertz, and the frequency of our sinusoid is about 20 hertz.
So let's put it at, it will be easier if I put it on, let's put it at 150. Let's see if we can shift the peak. It will be easier to read. It's F0, which is here, 150. Oh. Let's see where the peak goes. Close, but not. Maybe I miscompute something, but interesting. Oh yes, I think I know why. I have sampling problem of my signal itself. So let's fix that. You see, oh, it's a bit undersampled for identity, so let's try to fix that too. So we can, let's go to 2 kilohertz. Let's get a bit more oscillation. Maybe go to 5 kilohertz. Yeah, this one I just see if it's a better estimate. Yep, that works. You see, so now I think we have 1, 2, 3. So it's 1, 2, 3, 150. We got it.
If you want to shift your peak, you can use log. Because if you try in a linear scale to put it in the middle,
yes,
you will always have some problems with the same.
Yeah, absolutely right. So log, we can do that like this, just as easy. So Complot has a problem for log when it starts at 0. But we have the power of the iterator. So let's keep the first. Keep 1 means keep the first element. Et voilà. So let's use IPython to compute. Okay, no, let's do, yes, now it's the frequency is log 10 of the frequency. So np.log 10 of 150, 2.17. Yeah, that's where we are. So we have successfully implemented the Welsh algorithm in Rust. So we have a few minutes left. I think we're going to add some noise on our signal, the next thing. Maybe we won't have the time to do it now. So do you have any question on what we did here?
Yeah, so if you wanted to export that data now, is there an easy way to do that? Can you
Into
write
a
it
file?
straight to MATLAB or?
No, there's no easy way. If we go back to we'll see what's available in LibRS as format. If you look for I don't say there's no easy way, but there's ways to do it. So MATLAB, you have the MATFile here library, which is a library for reading and MATLAB MATFiles. It's pretty limited what you can do. You see, it just allows you to deal with numeric arrays. That's all they do. So you can do it. Can you?
So that's something that's still under development, it looks like. Or
If it looks like it is, yes. Loading a mat file. Look, can you write it? Can you? I'm not sure you can even write to a mat file. I'll have to allow you to load.
oh yeah,
Or you
it's
can
not
just
checked.
load. Writing mat file, it's not there. Okay, no, you can't. All right, that won't be good.
Is this the only option?
You can use CSV file. For MATLAB, it's pretty limited. For Python, for Python we can use Pickle. I've used Serly Pickle. It's pretty useful. So that you can read and write for Python. But for MATLAB, it's a bit limited. For simple, you can use CSV file. Let's go back to MATLAB if there's other options. Mat file enduring. Let's see if this one can write. Errors. Pour convertir mat file, il y aurait un erreur. No, it's not something
CSV
else.
files are usually much bigger, right?
Yes. Yes. No, it's not. With MATLAB, it's not great right now, the ecosystem to write data to MATLAB. You need to go with other format. You can use something also called HDF5, but it's not very friendly either. So, yeah, it's a bit limited, I would say, on that side.
I don't know to which extent it's hard to access Pickle files in MATLAB, but perhaps this could be an option. It seems what I have seen is that there are a lot of tools to integrate MATLAB with Python. So if it's not available, I believe that in the near future it will be.
So what I've been doing in the past when I want to go from Rust with relatively complex or a lot of data is I wrote with the Pickle library the data into a Pickle file, and then I open Python and I convert it from Python to MATLAB in Python, and that works. That I remember that I had the same issue at some point, and I started something. Don't know what I was doing.
Yeah, just did like a quick Google search, and apparently you can, if you set it up right, you can open it in MATLAB using a Python library.
So, yeah, you need to go through Python right now. I play a bit with that. I don't know the status of that. Open a mat file. So it's just reading. No writing. I'm not aware of anything that writes into MATLAB right now. You have to go through a Python format and then open that and convert that too. Because yeah, the interaction with Python is quite well done. You have, if you go to NumPy, instead of Pickle, you have also NPYZ, which is another Python format that I think Rodrigo is familiar with. You can write also to the NPY format. And NumPy is a numerical library, the equivalent of MATLAB in Python. You can write to their format too. And that also can be converted into MATLAB format, but within Python afterwards. So you're not stuck, but you need to know Python, or you need to know somebody who knows Python who can help you. And that's all for today. So
Okay, thanks, Rod.
yeah, you're welcome. Thank you. Here you go. So we successfully implemented the right algorithms. We get the right peak at the right frequency, and we can even do some plot. So next week we'll go through adding some noise to the signal. Like this, we have an idea how to add noise, white noise to the signal, and then we go back to the library where we spend a bit more time improving our library. So we'll go through maybe implementing things, starting to introduce lifetimes, traits, and this kind of thing that are important feature of the language that are important to be familiar with. All right. Thank you.
All right. Thank you.
Thank you. Bye-bye.